Welcome. This video is going to be explaining self-adjoint operators. We're going to be going for, well, about an hour and a half worth of mathematics. Care to sleep? Very well. Alright, we are going to begin. We are now going to be focusing on self-adjoint operators. Now, a self-adjoint operator is when you have V as an inner product space. A linear map T of V to V is self-adjoint or Hermitian if T adjoint is equal to T. T adjoint is, or T star, you have it being T transpose conjugate. Now, clearly, if T is self-adjoint, then T is normal. So, something being normal is when you have T star. T is equal to T star. Now, let us recall again the connection to matrices. Fix an orthonormal basis B for V, and let A equal to the transpose, the transformation in the basis B. Then T star B is equal to some sort of matrix A star by theorem 6.42. Therefore, T is equal to T star. If and only if A is equal to A star. Now, I'm going to post all of these notes for anyone who wants to in the description. We therefore introduce analogous terminology for matrices. Definition 7.12. A matrix A in the complex matrix space square version here is self-adjoint or Hermitian if A star is equal to A. Note that if A is a real matrix, A star is equal to A transpose, since Z bar is just equal to Z for all real numbers Z. A rotation 180 degrees, a rotation around 0 degrees is just going to be, well, itself. A real number lying over here is just going to go onto itself. Now, a matrix A in a real square matrix satisfying A transpose is equal to A is called symmetric. Now, symmetry in matrices is very important, and we'll talk a lot more about them in the fall as we go along. We start by showing that self-adjoint maps can only have real eigenvalues. Now, let's go through lemma 7.13. Let T of V to V be a self-adjoint map. Let lambda be an eigenvalue of T. Then lambda is a real number. How are we going to go about this? The proof goes like this. Let V be a non-zero eigenvector of lambda. Then lambda with V inner product with itself is the same as inner product of lambda V with V, which is the same as the transformation of V with V. Then we can move over T to have T star on the other side of the inner product with V T star of V. And since we know that it is self-adjoint, we know that T star is just equal to T, which is the same as V TV. Now, this next step, you could go a bit more into detail, where you understand that you have this inner product V, and you're going to have lambda V here. Now, to pull it out, because we are working over a complex space, this lambda, or eigenvalue, can actually be complex. And so to remove it, we will have to take the conjugate of it, and so you are going to have the inner product space of lambda bar V V. And then you're able to pull it out, and you're able to receive this result. Now, since V is not 0, we may divide the inner product of V and obtain lambda is equal to lambda bar. This implies that lambda is a real number. The main theorem we prove regarding self-adjoint operators is the following. 1 minute. V is not 0. We may divide, yes. We may divide by V, yes. That makes a lot of sense. Figuring part of this out as I go. Now we're going to continue to theorem 7.14, orthogonal diagonalization in real inner product spaces. Let V be a finite dimensional real vector inner product space, and let T of V to V, then the following are equal. Now, T is going to be self-adjoint. There is an orthonormal, since you could just take away the magnitude, right? Divide it by the normal, or the norm. Basis of V, consisting of eigenvectors of T. Thus, self-adjoint operators play a similar role in real inner product spaces as the role played by normal operators in complex inner product spaces. That is, they are exactly the linear maps which admit an orthogonal basis of eigenvectors. Now, to read this with my mind, instead of just my eyes, I'm going to go over it again. If V is a finite dimensional real vector inner product space, and we let the transformation of T of V to V, right, be a linear one, we're going to have T being self-adjoint is the same as there being an orthogonal basis of V consisting of eigenvectors, i.e. we're going to have an eigenbasis if T is self-adjoint. And that's why we go over again, saying, thus, self-adjoint operators play a similar role in real inner product spaces as the role played by normal operators in complex inner product spaces. That is, they are exactly the linear maps which admit an orthogonal basis of eigenvectors. Now, the proof of theorem 7.14 is similar to that of theorem 7.4, namely to show 1 to 2. We're going to argue by induction, taking an eigenvector of V of T and then restricting T to the orthogonal complement of V. The only missing ingredient is the fact that T has an eigenvector, namely that the characteristic polynomial has a root. While this is immediate over the complex field, since every polynomial splits over C, this is the fundamental theorem of algebra. It is not the case over the real numbers. Ooh, thank you for the follow, Floor Match 420. Nice to see you here. Nice to see you. Nice to see you. Now, we continue. This is not the case over the real numbers. Indeed, there are linear maps over the real numbers which have no eigenvalues. We show that if T is self-adjoint, then, even then, you have the characteristic polynomial splitting over the real numbers. Very, very convenient. Now, we're going to move to lemma 7.15. Let V be a finite dimensional real inner product space, and let T of V to V be self-adjoint. Then, the characteristic polynomial splits over R. The proof goes as such. Now, before we go over the proof, we're going to better or slightly better understand what's going on. V is a finite dimensional real inner product space, so that means these values, any input is going to be real, or it's going to be composed of reals, and let T of V to V, this transformation, linear transformation which we're working with, V to V, be self-adjoint. Then PT splits over R. Again, being self-adjoint is T star is equal to T. Let's continue. The proof goes like this. The idea is to consider T as a linear map over the complex numbers. Use the fact that every polynomial splits over the complex numbers, and then use the fact that all eigenvalues are real by lemma 7.13. However, it is not immediately clear how to make V a complex inner product space. There is a standard way of doing this called complexification, but we bypass this, instead passing to Rn via coordinate vectors and then considering Cn as the complex analog. Indeed, fix an orthonormal basis B of V, then A is defined as the transformation T in the form of a matrix of basis B, satisfies A is equal to A star, i.e. it is self-adjoint, as we saw above. Now, let the transformation upon the matrix A of Cn to Cn be the linear map given by T of A applied to the vector V is equal to the matrix A composed of V. Now, as we saw above, we have that this transformation in the standard basis is equal to the matrix A. Note that E is an orthonormal basis for the standard inner product on C of n. Hence, TA is self-adjoint with respect to this inner product. Indeed, TA, or transformation with respect to A star in the basis, or the standard basis, is equal to A star, which is equal to A since it's self-adjoint, which is equal to TA in the standard basis. So TA star is equal to TA. We know that the characteristic polynomial of TA splits over C. This is standard. Now, by lemma 7.13, all eigenvalues of TA are actually real, since TA is self-adjoint. Hence, the characteristic polynomial restricted to A, or with A, splits over the real numbers. Finally, we have PT of A is equal to characteristic polynomial, or the characteristic polynomial with respect to A, which is equal to the characteristic polynomial in respect to T, since A is a representing matrix of both TA and T. Hence, PT splits over R. Now, to somewhat simplify, the first part is trying to somehow make it that we run over into V being a complex inner product space. There's a way of doing this called complexification, but instead of that, we pass to Rn via coordinate vectors, and then considering Cn as the complex analog. So basically, take Rn, take coordinate vectors. Let me exactly figure out what coordinate vectors are. Oops. Didn't exactly go over that last bit. Position of a vector in an ordered list of scalars. Ah, column vector. Ah, I see. How did I not remember that? Something slip. And then we use Cn as the complex analog. We just pass over, or these real numbers, since they're in the complex, we pass them over as a complex number, even though they're reals as well. So we fix an orthonormal basis, B of V, take the transformation, such that we have this self-adjointedness. Then we move along this proof, showing that in a standard basis, since it's orthonormal, we're going to have this matrix A corresponding to this transformation of A in the standard basis. Now, doing some tricky math, we're able to eventually get that even when it's adjoint, right, in the standard basis, it's the same. Since it's self-adjoint, it's going to be equal to this matrix, and then you're going to get your transformation standard basis. We love orthonormal bases. Yes, they're extremely useful. Extremely useful are is an understatement. Quite the understatement. Now, funny enough, when it comes to proving or applying the Gram-Schmidt process to said orthonormal bases, that's when it gets quite crazy. It's gonna get oof. Proofs. Now, we are ready to prove theorem 7.14. The proof is very similar to that of theorem 7.4, and we will omit some parts which are identical. Proof for 7.14. We're going to travel from 2 to 1. Suppose that T admits an orthonormal basis of eigenvectors v1 through vn. Let lambda I be a real number, be that the eigenvalue of vi, where 1 is small or equal to I, is small or equal to n, so that tvi is equal to lambda I vi. As the proof in 7.4, we can show that T star vi is equal to the conjugate lambda I vi. Now, the proof is identical. Continuing. We omit the details. In our case, lambda I is a real number. So in fact, T star vi is equal to lambda I vi. Now, it seems like I may have missed putting on the music. How could someone fall asleep when there's no soft music playing in the background? Indeed. Just mentioning it, the amount of people on Twitch watching kind of exploded. It was kind of funny. Let's continue. Let's continue. Perfect. Now, continuing. This means that T star vi is equal to tvi, as we know via the self-adjointedness. For 1 smaller equal to I, smaller equal to n. Now, since T star agree on a basis, namely v1 through vn, which is our orthogonal basis of eigenvectors, we have that T star is equal to T, i.e. T is self-adjoint. We are trolling just a little bit, just a little bit. Are we, or we are? Which one is it? Which one is it? There you go. I got my program almost fixed. 2 more followers to the follow goal. Very nice. Now, for 1 to 2, we prove by induction on n is defined as the dimension v, that if T is a v to v is self-adjoint, where v is a real inner product space, then T admits an orthonormal basis of eigenvectors. This is going the other way. The base case of n equals 0 is trivial because, well, you don't have anything. Each of the 2i pi, happy Monday, y'all. Hello, each of the 2i pi. Haven't seen you in quite the while. Nice to see you. Nice to see you here. Then T admits an orthonormal basis of eigenvectors. The base case n equals 0 is trivial. For the induction step, suppose that n greater or equal to 1. By lemma 7.15, the characteristic polynomial splits over the real numbers. So let lambda be a real number, be an eigenvalue of t, and let v be a non-zero eigenvector of t. We put w defined as the span of v. This is going to be our more or less starting point. Since w is t invariant, and hence also t star invariant, as we said t star is equal to t, we get by corollary 6.48 that w orthogonal, box that in, is also t invariant. Also, t restricted to w orthogonal is self-adjoint. Now, because we know it's t invariant, we also know it's t star, and we also know it's t star invariant. T star invariant, also restricted to w orthogonal, is going to be self-adjoint. GG format 420. That's okay. I didn't. Yeah. Soapy, that's great to know. What am I gonna do? What am I gonna do with that? Like toast. Like GG. Good for him. Good riddance. I suppose. My history teacher told me that? Well, yes. Actually, now that you mention it, today is 420. Ah, right. Because they say happy 420, everybody. Yes, that does make sense. That actually explains it. Ah, right. I remember hearing that fact as well. I mean, Mr. Mustache Man is, I think his skull's in like a ex-Soviet museum. This is in a Russian museum still. Or something like that. So, good for him. Good riddance. Anyways, let's continue. Thus, by the induction process, T restricted to W orthogonal admits an orthogonal basis of eigenvectors v1 through vn-1, and then v1 through vn-1 with v is an orthogonal basis of eigenvectors of T. By the way, if we say that v1 through vn-1, this v is going to be something in an orthogonal, so it's going to be linearly independent. Now, because and to get the rest of the vectors, you just have to add v with one of these v1 through vn, and you get the rest of the basis, or you get everything else for the orthogonal of the orthogonal, or the standard w. Now, just like in the case of theorem 7.4, theorem 7.14 can also be stated in the language of orthogonal projections, i.e., in analogy to theorem 7.9, namely for self-adjoint operator T over a finite dimensional inner product space with distinct eigenvalues lambda 1 through lambda r in the real numbers. We could write the transformation T as the sum of your lambda i's, pi's, where pi is the orthogonal projection onto the eigenspace, lambda it. Remember, the importance of the eigenspace is where you have t minus lambda I, and then, for example, the v is going to be equal to 0. Right, so where we have, tv minus, tv minus lambda I, tvi, there you go, is actually equal to 0. So the point of that is that it's really easy for the polynomials that if you have whatever polynomial, one of them being equal to 0 nukes the rest of it out. Let's continue. Lemma 7.16. Second. Let V be a finite dimensional, real, or complex inner product space, and let T of V to V be self-adjoint. If T of V with V inner product space equals to 0 for all V and V, then T has to be 0. Now, over the complex field, Lemma 7.16 holds without the assumption that T is self-adjoint. Indeed, there was a question in tutorial 6 where we proved that TV of V is equal to 0 for all V and V for a linear map T over a finite dimensional complex inner product space V. Then T is equal to 0. Now, for the proof of lemma 7.16, I could go over the proof of the theorem that we learned in the said tutorial. However, we are going to work over it, not right now, but right now we're going to go over well, probably as far as I can really go, into the end of singular value decomposition and polar decomposition. Well, most likely because I have an exam in not too far from now. So, you know. Anyways, let me continue. So, the proof of lemma 7.16. We need only the fact that t is diagonalizable, which holds by theorem 7.14. So let v1 to vn be a basis of eigenvectors for t. Let lambda 1 to lambda n be the corresponding eigenvalues. You will not need the fact that v1 to vn are orthogonal. Then, tvi, inner product with vi is lambda I with vi, when you pull out lambda I and vi with vi. Now, on the other hand, tvi with vi is equal to 0 by assumption. Since vi with vi is not 0, it has to be that lambda I has to be 0 for all I. Hence, t is equal to 0. Because tvi I is equal to lambda I vi. Now, if vi times vi, which is the inner product, is not 0, then for lambda I vi to be equal to 0, you have to have this lambda I, well, lambda I has to be equal to 0 explicitly. So then when it's 0, lambda I vi times vi is also equal to 0. And since tvi is equal to lambda vi, right, this component is the same. This t part, right, this transformation is the 0 transformation, i.e. the mathematical nuke. Now we are going to work over unitary operators. Let me get a quick look over how long these unitary operators are, because if it was as short as 7.2, I may be able to actually, probably going to be able to get all the way to the end. Yeah, I may actually be able to get to the end today with decent space, and we could start the computation jam. That'd be really, really awesome. Okay, yeah, that's actually exceptional. That's exceptional. By the way, what was I gonna say? Yes, if anyone wants the material on which I'm working, I can send it in the Discord. Please tell me if you want it, and you can join the Discord if you want. It'll be posted in the link in the description for those who are watching on YouTube, if you're not asleep yet. Now, we consider another important class of normal operators. Definition 7.17, the unitary operator. We have covered unitary operators on stream earlier before, where t star is equal to t star t, which is equal to the identity. Now, this is actually quite convenient. Now, in the meantime, we're going to explain along. Let V be an inner product space. A linear map, T of V to V, is unitary if t star t, or is equal to t star, which is equal to the identity. In other words, t is unitary if t is invertible, and t inverse is actually just its adjoint. Which, for those who are coming to stream right now, t star is equal to t transpose orthogonal. Let's continue. Note that if t is unitary, then so is t star. Why? Well, the same reason, because t star is equal to t star t is equal to I. Then you just replace t star, right? You just look at this side instead, or this middle piece, and then you just transform it to this piece if it's equal to I, and then you just get I, which is pretty straightforward. It's important. I think it's important in textbooks or even in notes to make sure to stop the reader and ask why. It's actually quite important. Let's continue. We also know that over the real numbers, unitary maps are also called orthogonal. As before, we can make the analogous definition for matrices. Definition 7.18, a unitary matrix. A matrix A in the complex numbers, or using complex entries of size n by n, i.e. a square matrix, is unitary if A star is equal to A star A, which is equal to I. Now, this is typically quite convenient. Note that a unitary operator is in particular normal. Why? For those of you who are remembering what normal is, it is when, let me remember, I'm pretty sure it had to do with t star t as well, and I'm pretty sure it was when t is equal to t star. Let me just absolutely remember, because, well, things slip. Let's see the definition of normalcy or normality. for those of you who hear a bit of a commotion outside, it's because, I mean, it got quite annoying. I mean, it's quite annoying that this is the exact time that people who the leaf blowers come by, even though there's no leaves to blow. Yep. Okay, yeah. So it is t star z is t equal to t star t. Okay, perfect. That is a normal operator. Let us continue along down. Here we go. Now, we now observe that the product of unitary maps is itself unitary, and the inverse of a unitary map is unitary. Hence, unitary maps form a group. Now, what's convenient about this is a group has, from what I remember by the definition of a group, any item with an operation applied to the other item, right? It is going to have an inverse. It is going to have it's going to have a, if it's a Boolean, it has addition and multiplication in the standard sense. But the standard definition of a group, I want to make sure not to mess up my definitions here. Yep. Okay, perfect. Set with an operation that combines any two elements of the set to produce a third element within the same set. Okay, perfect. So it stays inside. Things stay inside the set. Alright. Perfect. So it has associativity, identity, and an inverse element. Okay, perfect. Whoops. Let's continue with the lecture notes. 1 second. Right by our house. Let's continue. Lemma 7.19. Actually, we're going to go over the footnote 64, which is from a bit higher. Now, let's continue. Alternatively, in a real inner product space, one can prove lemma 7.16 by expanding t with u plus v. This is going to give us linearity. Indeed, using linearity, 0 is equal to t u plus v, and then inner product space with u plus v, tu plus tuv, tuv, tvu, tvv, which is equal to tuv plus tvu, right? Because your tu and tvv are going to be your, I guess there's 0 operators here, which is equal to tuv plus vtu equal to 2tuv. Using that t is self-adjoint, and then we're working over the real number line, so we do not need to take conjugates when swapping the coordinates of an inner product space. Thus, tuv is equal to 0 for all uv, which implies that tu is equal to 0 for all u. This gives another proof of lemma 7.16 in a real inner product space. As mentioned above, in a complex inner product space, the lemma holds by any map T without assumption that T is self-adjoint. Continuing, for lemma 7.19. Continuing, yeah. If ST of V to V are unitary, then ST is unitary. So if S and T are individually unitary, then ST is unitary. So, I mean, we're going to prove it really quickly down below, so I'm not going to bother proving it right now without looking at it. If T of V to V is unitary, then T inverse is also unitary. If it's unitary, then we know that T minus 1 is equal to T star, but we're going to prove this now. We use the proposition 6.45 for item 1. ST times ST star is equal to ST times T star S star, which is equal to S star, which is equal to the identity element. Now, because we have T star, this is the identity, right? This is just equal to, in this middle part, the identity. Then SS star, is also equal to the identity. Now we have ST star, ST. Well, you're just going to get this inner side also being the identity, and this outer part just all being the identity. Now we have T inverse star is the same as T star inverse, which is equal to T inverse, which is just, well, T, which shows that T inverse is unitary, i.e. its adjoint equals its inverse. Now, it turns out that unitary maps have many equivalent characterizations. The main theorem we prove is as follows. This is going to be most certainly an important one for the upcoming exam of mine. Let V be a finite dimensional or real complex inner product space, and let T of V to V be a linear map. Then the following is equal. T is unitary. Du, inner product space, TV is equal to UV for all UV in your vector space. The norm of TV is equal to the norm of V for all V in V. There is an orthonormal basis, V1 through Vn, V, such that TV1 through TVn is also an orthonormal basis. For every orthonormal basis V1 through Vn of V, the set TV1 through TVn is also an orthonormal basis. Now, this is all a lot to digest and a lot to handle immediately, so let us go and prove this carefully, because mind you, these proofs are are more or less short. Like, at least for the first couple of proofs, for the first 3 or 4 proofs are short, but then then a couple, I'm pretty sure a couple of them get quite long. So we'll show 1 to 2 to 3 to 1, and 2 to 5 to 4 to 2. Right? So basically covering all of our bases. Now, we'll start with 1 to 2. For all u, v, and v, we have that tu, tv is equal to u. You see this self-adjointedness? Identity is equal to uv. Pretty straightforward. Or unitary, unitariness, unitary capabilities. Master of English. Third language. 2 to 3. This is immediate. Simply apply item 2 with u equals v, right? And you get the t star and then uv, so you're going to get the normal v squared, right? You just replace u with v and you get vv. Pretty straightforward. I mean, what can I even say? Right? The TV squared is like, I mean, not much to explain here, folks. Now, 3 to 1. Suppose 3 holds. Then we have t star t v in inner product of v is tv which is equal to vv. Now, for those of you who are trying to remember what 3 is, norm of t v is equal to v. Now, this was the norm of tv squared, or tu tv, uv, and then you just plug in v for both sides and you get the item squared. So, pretty straightforward, right? That's how we get 2 to 3. Now, moving from 3 back to 1 is assuming 3 already holds. You want to go back to it being unitary. So, what we did was taking t star t, v, composed with v, since mind you, this is the identity element. Then we're able to move this t star over to get tv, which just gets you vv, i.e., you get your unitarity. Oh, there you go, I think that's a better word. So t star t minus i, 0 in this case. V, composed with v, is t star t v, v inner product v minus v composed with itself. I.e., you multiply this one and this one by v, you get your t star t v minus iv, inner product with v, get that on the inside, and because of linearity, we're able to split it up, and we're able to move it to 0. Expanding a few steps. Famished integral. Math streamer? I like the people lol. Yes, hello. Also, thank you for following famished integral. Famished integral? Yes, that's how I spell your name. I'm sorry, I kind of have like my notification, my pop-up sound kind of nuked, so I have to like figure everything out. In the meantime, let me actually just look. Yes, no, I don't think that's actually gonna work. I have to. I'll see what goes. Alright, one more follow until I actually reach the follow goal. That's actually quite cool. Let me just do you? There you go. Now, for all v and v. No, you have 0 to for all v and v. Remember, you got the 0 and 0 composed with v is 0. This whole thing is 0. This whole thing has to end up being 0. So obviously ends up being 0. And yet we work with them in unitary. So therefore we see this unitary. Everything here is, well, works out being to be unitary. Now, next observe that the map S defined as tt star minus I is self-adjoint. Indeed, t star t minus I star is t star minus I star, which is going to give you t star, right, because, well, composed with t star because you're gonna star the star, and then you inverse it, right? So you get your t goes back, right? It ends up on the other side, becomes starred. T star star which is just t minus I, right, as we see, and so you get t star t minus I. Now, since SV, v is equal to 0, for all v and v, include by line of 6.7.16 that s is equal to 0, meaning that t star t is equal to I. Therefore, t is unitary as required. For convenient. 5 to 4, this is immediate. For those who remember, you have an orthonormal basis, then you have the set TV1 to TVN is also an orthonormal basis, right? So there is an orthonormal basis such that TV1 to TVN is also an orthonormal basis, and you already have this. If this is true, then because you have this is orthonormal basis, you already have this orthonormal basis ahead of time, so obviously this ahead of time piece works. So this is the forward direction, this is the backward direction, and the backward direction already exists, right? You're just retracing your steps. So 5 to 4 is done. Now we're gonna go 2 to 5. This is also immediate. If 2 holds, for those who remember, 2 is tu tv is equal to uv. Oops. Okay, there we go. Then tvi tvj equal to vi vj, and using the Kronecker delta, you're only going to be left with a vj and vj for any orthonormal basis v1 through vn, implying that tv1 to tvn is also an orthonormal basis. From 4 back to 2, since 4 holds, right, assuming 4 holds, there's an orthonormal basis b. One second, what goes to 4? Do you just assume 4 always? Oh, right, because 4 is, if you already have this, then it is going to apply. So you don't need to prove 4. You assume 4 from existence. You assume it to exist. Now, 4 to 2. Since 4 holds, there's an orthonormal basis b, v1 to vn, such that c is going to be tv1 to tvn. It is also an orthonormal basis. Let uv in v, and note that tu in the basis c and u is equal to u in the basis b. And similarly, tv in the basis c is equal to v in the basis b. Indeed, if u is the sum of your ai vi, where your ai is a scalar, then tu is just ai t applied and tvi. Similarly for v, since b is orthonormal. So basically what we're doing is you following Corollary 6.19, let me finish this. We have uv is equal to u in the basis b, v in the basis b. Similarly, since c is orthonormal, Corollary 6.19 gives tu composed with tv is equal to tu in the basis c, inner product with tv in the basis c. But tu in the basis c equals to u in the basis b, and tv in the basis c equals to v in the basis b. Right? For those of you who are catching this, since you have tu in the basis c, it's going to be, we're going to trace back to some item which is in the orthonormal basis. tv in the basis c is going to be v in the basis b as well. So u in the basis b, which is the same as tu in the basis c, v in the basis b, which is tv in the basis c, as just shown, it follows that tu tv is equal to uv as required. Now, next we show that all eigenvalues of a unitary map must lie on the unit circle. What? All eigenvalues of a unitary map must lie on the unit circle. Oh yeah, right, because you can do the cosine, because you do all these cos work, all this trig stuff within, so yeah, it has to be able to lie on the unitary circle. Now, this gets a lot nicer once you actually start working at that point with toruses, and then you get some Mobius strip work, and then it all starts to unfold. It starts to go cookie crazy. Let's continue. Yeah? Gotta show off this little... Nice. Oh yeah, right, if the music is playing in the background, you guys got a bit of that music for the... to help soothe you into a slumber. Let's continue. Now, we work with proposition 7.21. Man, the best ASMR to make is when you take the microphone, you put like a cheese grater, it funniest thing in the world, especially when that guy who had a Spider-Man costume when he did it. GG. Let's continue. If t is unitary, then every eigenvalue lambda of t satisfies that the absolute value of lambda is equal to 1, i.e. we are working with something which we're working in a unit circle, or working on an orthonormal. We're just gonna have to do with that scalar, so I guess, are you gonna be working with orthonormal? Let's actually figure that out. Proof. Let v be a non-zero eigenvector of lambda. Then tv composed with tv is lambda v, which is lambda times the conjugate of lambda, which, if you remember, this is actually just going to be lambda, absolute value of lambda squared. And we have v composed with v, so we're just going to maintain that. On the other hand, by theorem 7.20, which we covered recently, we have tv composed with tv is equal to vv. Hence, lambda squared vv is equal to just vv, i.e. lambda squared has to equal to 1. Now, we will finally consider unitary matrices. As stated above, a matrix in the complex square, a matrix field, I suppose if you want to call that, is unitary if A star A is equal to AA star is equal to the identity matrix. For real matrices, this becomes A transpose A is equal to AA transpose, which is equal to identity. And such matrices are also called orthogonal matrices. We proved the following characterization of unitary matrices. Theorem 7.22. For a matrix or square complex matrix, the following are equal. A is unitary. The columns of A form an orthonormal basis of C to N. Very convenient. The rows of A form an orthonormal basis. Interesting. So, this is a basis in the complex scale, or complex field, and this is an orthonormal basis. Okay. So both are bases. Bases? Yeah. Interesting. It's actually quite convenient. We may actually have to use, or we may actually use the fact, I might write a cheat sheet, which I'm going to use for this. It's actually going to be quite convenient for when I actually have to apply it. Alright. Continue. I want to make sure that I'm able to actually reach my follower goal. Though once I reach the follower goal, I don't accidentally miss it because, well, the sound for me is working funny for some reason. I don't know. We'll figure it out. Let us continue. Proof. Next, we just started. Denote the rows of A by R1 through Rn, right? These rows, and columns of A as C1 through Cn. Note that AA star ij is the same as AIK, maybe with I being the column element and K being the row element, times A star of Kj is the same as AIK A hat JK. Why? Because it's transposed. We move KJ to JK, and we bar it, which is what the definition of this starring does, which is row I inner product space with row J. Now, similarly, A star A IJ is equal to A star IK times A KJ, which is equal to, as you can see, again, transpose conjugate, boom, times A of KJ, which gives you the column CJ, the column CI, excuse me. By definition, A being unitary means that AA star is equal to A star A, which is equal to I. Also, is enough to require only one of AA star equals to I, or A star A equals to I, since each of these qualities implies the other. Now we see that if A is unitary, then AA star IJ is equal to A star A IJ, which is equal to the canonical delta. And hence, both R1 through Rn and C1 through Cn are orthonormal bases, right? Again, the canonical delta IJ is the function where 0 if I is not J, and 1 if I equals J. Yeah, give a bit of a line. There we go. Now, then A star equals I, or A star A equals I respectively, implying that A is absolutely unitary. That concludes unitary operators. We finished self-adjoint operators today and unitary operators today. Now we're going to go over positive semi-definite operators. Whoop. There we go. The program I made occasionally crashes and then automatically reopens. It's actually quite convenient. If anyone's wondering, it actually helps me run these PNGs. It has hand recognition, face recognition, kind of does everything. I actually made it myself. So, if I was wondering. I mean, anyways, let's continue. 7.4. Positive semi-definite operators. Recall that if a linear map T is self-adjoint, then all eigenvalues of T are real. This is what we've done quite a bit earlier at this point. Here we consider as special cases, here we consider a special class of self-adjoint operators. Little typo completely threw me over. Namely, those all of whose eigenvalues are non-negative, i.e. 0 or greater. Such operators are called positive semi-definite, or PSD for short. We shall in fact be given a different definition of these operators, not via eigenvalues, but we will then show that this definition is equivalent to all eigenvalues being non-negative. Oof. Quite a read here when you have typos, but let's continue. Definition 7.23. Positive semi-definite operator. Let V be an inner product space. An map T of V to V is positive semi-definite, or PSD for short, if T is self-adjoint and T of V, composed with V, is greater or equal to 0. If you remember, if T of V, we had something being equal to 0. If you remember, from when we were proving these, the following are all equal, we had T of V is equal to V for all V and V. Now, part of it, or one of the proofs we went over, was the fact that if you have T star TV composed with V and TV is composed with TV is equal to VV, or sorry, it was slightly different place where we had all of it having to be equal. If it's equal to 0, then it has to be that T is equal to 0. It's actually, I'm pretty sure, a bit higher up. Yes? Pretty sure it was. Yeah. So yeah, if TV with V is equal to 0, right, then T is equal to 0. We explicitly went over this by the fact that that VI with VI is not 0, right? In the case where it is, then we know that T has to be 0 because lambda has to be 0, and since we're working with eigenvalues, Ti is equal to lambda. TVI is equal to lambda I VI. Let us continue. Scroll down. Perfect. Remark 7.24. Similarly, T is called a positive definite if T is self-adjoint and T of V, inner product space with V, is greater than 0. Might not that it loses the semi-definite and becomes just definite for all non-zero V in V. One can similarly define the notions of a negative semi-definite and negative definite operator, requiring that TV composed with V is smaller or equal to 0, and that TV inner product space with V is smaller than 0 for all non-zero V, respectively. Note that T is negative semi-definite if and only if negative T is positive semi-definite, and similarly, T is negative definite if and only if negative T is positive definite. Now we're going to move on to the next remark, 7.25, and we're going to move on to definition 7.26. We should caution that some authors use the term positive to mean positive semi-definite as per definition 7.23. As usual, we can make an analogous definition for matrices. So this is more like two mini remarks in one. So those who say the term positive to mean positive semi-definite are kind of, I wouldn't say mistaken, but it's definitely a bit of a risky play to say, especially because you could have, well, 0 as a big chunk of it. But then again, what can I say? You know, hands up. Let's continue. Definition 7.26. Positive semi-definite matrix. A matrix A in the complex number n by n, i.e. a square complex matrix, is positive semi-definite if A star is equal to A, and AX, X, right, in the inner product, is greater or equal to 0 for all X in the complex number, or x being a vector in the complex number with complex field. Complex vector space. My. Today's a bit of a mess up your words day. GG. Let's continue. Claim 7.27. Let V be a finite dimensional inner product space. Let T of V to V if B is an orthonormal basis of V. Then T is positive semi-definite if and only if A is defined as T in the basis B is also positive semi-definite. Now, so proof. The proof we're going to go over is, since B is an orthonormal basis, we have that T star in the basis B is equal to A star. We've done this, we've proven this before on stream already. So by theorem 6.42, T star is equal to T. Yep. And TV, you can now make this the TV in the basis B, and V in the basis B is going to give you the matrix A times V in the basis B, inner product with V in the basis B. We've worked with this. We've done this countless amount of times. Make a transformation into a matrix. This shows that TV inner product space with V is greater or equal to 0 for all V and V, if and only if the same thing applies to the matrix when applied. For all X in the complex vector space which we're working with. Now, proposition 7.28. Let V be a finite dimensional, real, or complex inner product space, and let T of V to V be a self-adjoint operator, i.e. T star is equal to T. Then the following are equivalent. T is positive semi-definite, and all eigenvalues of T are non-negative. This actually becomes exceptionally convenient. We will show later. And now, for those of you who are afraid with what's going on below over here, trust me, it is not that difficult at all, and just uses a bit of substitution. Now, also for those of you who are going to be watching on YouTube and don't have that much experience with linear algebra, this is more meant for you to fall asleep. Those of you who have experience with linear algebra can probably already sense that I am not as, let's say, professional. And those of you who are in the middle and trying to learn something, hello. Like and subscribe. Let me get the There we go, got the pose. The hand tracker isn't working right as well because I have the microphone in hand. Let me move the microphone aside just to test it. There we go. Got it stable. Yep, just gotta move the mic away from my setup. Alright. That was the unannounced break. Proof. STF is self-adjoint if it emits an orthonormal basis of eigenvectors v1 through vn, and all eigenvalues of t are real. ST is self-adjoint if it emits an orthonormal basis of eigenvectors v1 through vn, and all eigenvalues of t are real. Let lambda 1 through lambda r be real numbers. So we already said that eigenvalues of t are real. Let lambda 1 through lambda n be real numbers. Sure. Be the corresponding eigenvalues. Right. This is supposed to be eigenvectors, I'm pretty sure. But by all means. Namely, tvi is equal to lambda I vi. Now, let us consider any v in V, and write V is equal to the sum of your alpha I, Vi, then TV composes V is equal to T, and you have your alpha I, Vi, inner product space with alpha I, Vi. Remember, with alpha I is a scalar, Vi is your vector, and you're just applying T. Remember, we defined V as this alpha I, Vi. This is just the sum. Now, this is the same as writing, just applying and bringing T on the inside. And since we defined TVI as lambda I, Vi, we put it in here, And now we have these two scalars working together, best friends. This is applied to vi, and you have your ai vi, which is equal to a lambda I ai j bar I, by the way, because we have, this is the inner product space, and we're trying to move the ai on the outside of this. Now what we're going to do is you have your vi vj, and because we're working with an orthonormal basis, we use the Kronecker delta. I've shown this Kronecker delta many times, but what it does here is basically it's going to nuke everything where vi is not vj, and so it's everything where vi is, or sorry, where I is not j, where I is not j, is going to imply that you're going to have everything as 0, so you don't add anything. Remember, the sum symbol, I know everyone, or most of the people watching already know what the sum symbol is, but just to remind you, you're just adding all these items from 1 to n, right, listed, like, so you add the first item, second item, etc., to your vnth item. That's about it. Now, then we use the star, right? Okay, it explains later. When I look at something, I see only that exact spot, so I'm actually not seeing the majority of the writing. I'm looking very, very particularly at a certain piece of the writing, funny enough. So then we have the summation of your lambda i's and your ai, right, squared. Remember, because an item times its conjugate is going to give you the absolute value of it squared. Let's see what else. Yeah. Here in the result, we use the vi vj is equal to using the Kronecker delta. Thus, if lambda 1 through lambda n are greater or equal to 0, then tv composed v is equal to, and mind you, by the way, this is going to be equal to 1. Where it's not equal to 0, it's equal to 1. So when you multiply this by 1, you're only going to get these values in the summation. I must have forgotten to explain it earlier. My. Now, then you have tv, inner product with v, is equal to lambda I ai squared, or the absolute value of ai squared, which is greater or equal to 0. So you see that if lambda 1 through lambda n is greater or equal to 0, then tv, inner product space with v, is greater or equal to 0 for all v and v, meaning that t is positive semi-definite. Conversely, suppose that there is 1 small equal to I, small equal to n, such that lambda I is smaller than 0, strictly smaller than 0, by the way. We're going to show why. Because, okay, I'm just going to show why now. Because if it was greater or equal, then you'd have your positive semi-definite, so we're looking explicitly at the smaller than 0 case. Then to vi equals to lambda I, vi equals to lambda I, vi, which is smaller than 0, meaning that t is not positive semi-definite. Remember, vi is strictly greater than 0, because what you do here, because vi squared is explicitly greater than 0. Otherwise, you have some sort of item squared, right? You have some sort of vi squared, which is smaller than 0. This only works, I guess, in some back alley field, or maybe in the complex numbers. Who knows what kind of crazy behavior you gotta exhibit for an item squared to be smaller than 0. Like, you really gotta, well, I mean, you know, square root of -1 squared is gonna be, it's complex, right? And we're working with real numbers here, so, you know, here we're working with vi is going to be expressly greater than 0. Oh yeah, by the way, it's just a cool thing I found. I to the I is actually a real number, so I thought it was actually pretty cool. I've seen the proof. It's some really crazy stuff, right? And it gives you some like really fancy number. Oh, and Stuki rubs eyes. Good morning, chat. Oh my gosh, and Stuki, hello. It's 3:29 EST. So for me, it's like midday. So I'm quite surprised that rubs eyes. I mean, maybe you took a nap, maybe you woke up. I don't know. But yeah, hello, nice to see you. Get the hand wave. I need the right art now to be able to show a hand wave. I got hand motion. Found. I was able to code in the hand motion. What am I saying? So I'm able to pull off poses like this. There we go. I have to decrease the sensitivity for the accuracy of that one. I'm able to put like accuracy sensitivity, so I needed just a bit more with that. I actually got my first 1-bit donation yesterday, 2 of them. Yesterday, Friday. I still can't like stop thinking like thank you to Anders, okay, Anders, like and like, thank you, bro, for the Twitch handle. So thank you again for the first donos. Anyways, let's continue. Let us continue. So we observe that for every linear map T, the map T star T is positive semi-definite. We shall later see that in fact every positive semi-definite operator has this form, infinite dimension. Now, OMG Anders, what a bench. Yeah. Very much mensch. Very good mensch. Well, yeah. I mean, what can I say? He's exceptionally kind. I think I got a total of like what 3 bits from him. He was very kind. It's because I have whoops. I'm gonna go stream manager. There we go, stream manager. It's because I have this stickers. I have stream stickers that for 1 bit you could throw things at me. For those who are interested, stream stickers, and then you can throw me at me. And it says see Andrew. Okay, he gave me 2 bits. Still, really awesome from him. Let's continue. Now let's continue. Proposition 7.29. Let VW be inner product spaces and let T of V to W be a linear map. Then, the map T star T from V to V is positive semi-definite. So, okay, let's see. What was I gonna say? Ah, yes, I was probably gonna... What was I gonna do? Probably continue. No, I was thinking of doing something slightly off topic, but we're not doing anything off topic. We're doing everything on topic today. Oh yeah, right. By the way, it's 420 today. For those who find that date special for themselves, happy 420. Smoke weed every day. Anyways, first T star T star is equal to T star T star star. I'm saying star more than I thought, but yeah, it's because you have ST. Star is equal to T star. Oops, T star. S star. So you get this, which is equal to T star T. So T star T is self-adjoint. Second, for every V in V, we have T star TV is equal to TV TV. Remember, you can move this star over. It's the same as, I guess, it's like moving things over, which is greater or equal to 0. Hence, T star T is positive semi-definite. Now, second, a key property of non-negative real numbers is they have square roots. And the square root can be chosen to be non-negative itself. We now show that PSD operators behave analogously. 1 second. Key property of non-negative real numbers, yeah, and they have square roots. Yes, they do. Yes, everyone say hello to Instuki. Hello. We now show that PSD operators behave analogously. Every PSD operator has a square root. Moreover, the square root can be chosen to be positive semi-definite itself. This is going to lead into the singular value decomposition of polar decomposition, which is simplifying any matrix, like any, I guess, rectangular matrix, right? Because if you throw me a triangle matrix, I've seen some particularly talented individuals have a matrix like this. These be your 3 corners of your matrix, or you have your pentagonal matrix. This one looks more like a star, right? Or like your hexagonal or your whatever polygonal matrix, which is quite insane in my opinion, right? But to each their own, I suppose. Maybe there's some use to it. I know like people find uses for basically everything in mathematics, but I don't know. Does this thing even have a use? Like it could like different shape for matrices. gonna draw something real quick here. Little connections between these two. 3. Kinda. I don't know. I don't know exactly what I'm making here, but it's gonna connect all the points. Gonna connect all the points. Alright, you guys can figure out what it is from here. Hey fam. Hello. Hello, very much back to the starved integral. A starved collection of infinitely small rectangles which add up to an area. Let's continue. Proposition 7.30. Let V be a finite dimensional or real or complex inner product space. And let T of V to V be a positive semi-definite map. Then there's a unique positive semi-definite map, S of V to V, such that S squared is equal to T. I.e., because lambda I is in the real star, you have that the square root of lambda I is also a real number. Right? So, I mean, this is the most straightforward version. I know this R star looks pretty sped, and this star means that it's 0 and up. I know it's mathematics doesn't really have that. It doesn't have like a 100% solid, I guess, frame or symbology notation. The same way physics doesn't. Physics is notorious for that problem, but you know, not gonna judge the physicists because they are absolutely cracked. So, you know, hands up to them. They're awesome. Let's continue. Proof. As T is positive semi-definite and hence self-adjoint, which is kind of under the definition, it admits in an orthonormal basis v1 through vn of eigenvectors and eigenvalues of T are real and non-negative. So let lambda 1 through lambda n be greater than or equal to 0. Be the corresponding eigenvalues, namely TVI is equal to lambda I VI. Define a map S of V to V by setting SVI defined as the root of lambda I VI, where the root of lambda I is the non-negative root of lambda I. Little hint, we're going to use sigma as representing this root lambda I. So if I start laughing at nothing, it's most likely because I'm laughing because sigma mog male, something like that. Or it just suddenly became funny again. Then they see us in the club. Dun, 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 dun. Anyways, here we use that we may specify a linear map in a unique way by specifying the images of the elements of a basis. And v1 through vn are eigenvectors of S with eigenvalues root lambda 1 through root lambda n, respectively. Crucially, for every 1 small equal to I small equal to n, we have that S squared vi is equal to root lambda I square vi lambda I vi is equal to tvi. Hence, since S squared and T agree on the basis v1 through vn, we have that S squared is equal to T as required. Let us now show that S is positive semi-definite. First, S has an orthonormal basis of eigenvectors, namely the basis of v1 through vn, and hence S is normal by theorem 7.4. Remember. So, yeah. Continuing. Since S only has real eigenvalues, it follows that S is self-adjoint. And since the eigenvalues of lambda 1 through lambda n, they're all written individually, of S are non-negative, we get that S is positive semi-definite by proposition 7.28. Look at all the work we put in actually coming to use. Now, I'm going to read 65 before we move on. Alternatively, one can show that S star vi is the conjugate or the bar of lambda I with vi, composed with vi, which is just the root of lambda I vi because it's real. Indeed, we did a similar calculation to prove theorem 7.14, which shows that S star vi is equal to SVI for all 1 small equal to I small equal to n, and hence S star is equal to S, meaning that S is self-adjoint. Ta-da! Ooh, scam call. No. Let's continue. So, we proved that... Oh, yes. So far, we proved the existence of a PSD, or positive semi-definite, square root of T. Note that the positive semi-definite square root of S that we found satisfies for every eigenvalue lambda of T and for each V in the eigenspace lambda T. It holds that SV is equal to root lambda V, Also, there exists exactly one map of S satisfying this, since V is the sum of eigenspaces of T as T is diagonalizable. We now prove that the positive semi-definite square root of T is unique. So, suppose S is a positive semi-definite map satisfying that S squared is equal to T. Let V1 through Vn mean orthonormal bases of eigenvectors for S, and let mu1 through mun greater equal to 0 be the corresponding eigenvalues. Then TVI is equal to S squared Vi, which is equal to mu I squared Vi, meaning that V1 through Vn is also an orthonormal basis of eigenvectors of T. Also, if we denote the eigenvalues T by lambda 1 through lambda n, so that TVI is equal to lambda I Vi, then lambda I is equal to mu I squared, meaning that mu I is equal to the root of lambda I, where lambda I, of course, denotes the non-negative root of lambda I. Here we use that mu I is greater than or equal to 0, which holds as S is positive semi-definite. It follows that for every eigenvalue lambda of T, and for each V in this eigenspace of lambda T, it holds that SV is equal to the root of lambda V. Therefore, S equals the positive semi-definite square root that we defined. This proves uniqueness. Very nice. We will denote the unique positive semi-definite square root of T by T to the 1 over 1 half, or the root of T. Mark 7.31. Okay, and then we get to the single value decomposition and polar decomposition theorem. Okay, in that case, let's continue. 7.31. Being positive semi-definite is clearly not necessary in order for a linear map T to have a square root. For example, over the complex, every diagonalizable map has a square root. Wait a minute. Yeah, this can be shown by using the same proof as proposition 7.30. Also, some non-diagonalizable maps also have square roots indeed. Indeed, trivially for any linear map T, the map T squared has a square root. It turns out that one can characterize the maps having square roots via the Jordan canonical form. In fact, over C, a Jordan block of type lambda not equal to 0 always has a square root. And so the problem reduces to considering nilpotent maps. i.e., we only need to consider the generalized eigenspace of lambda is equal to 0. So one can characterize nilpotent maps having a square root. We will not cover this. Oh well. But yeah, if nilpotent maps have a square root in themselves, this I'm pretty sure leads up to the Lie algebras, because if you're able to decide decisively make matrices themselves items on which you can operate, then it just ends up being that that you could just use Lie algebras, just basically make matrices their own thing per se. Anyways, let me finish. In any case, being positive semi-definite is necessary for having a positive semi-definite square root. Because if a linear map S is positive semi-definite, so is S2, or S to the 2. Why? I mean, if it's positive semi-definite and you have your S squared, since it was S is equal to root of lambda I, or I guess mu I, my gosh. In case being positive semi-definite is necessary for having positive semi-definite square root. The linear map S is positive semi-definite, and so S squared, where we show just above that S squared is equal to T, where T Vi is equal to lambda I Vi. We also have SVI is equal to the root of lambda I Vi, and so when you square it, you're going to have lambda I Vi, which is just your transformation TVI. That's about it. Nothing crazy. Corollary 7.32. Let V be a finite dimensional, real or complex inner product space. Let T of V to V be a positive semi-definite map. Then there's a map S of V to V such that T is S star S. Proof. Let S be T to the half, then the positive semi-definite square root of T, square root of T. Then S squared is just equal to T. And also, S is self-adjoint, meaning that S star is equal to S. Thus, S star S is equal to S squared, which is equal to T. Pretty straightforward. That's going to be the end for today's, for the YouTube video. And if you want to pop up on stream to see the rest, I'll be very glad. This was about an hour and 15 minutes of linear algebra to fall asleep to. Take care, like and subscribe. See you in the next one.